Welcome to the Explainer. Today, we're jumping straight into a really fascinating 2026 paper by Dan Adrian German. It's called A Term-Rewriting Semantics for Pure Quantum States. Now, I know that title is a bit of a mouthful, but at its core, this paper takes one of the most notoriously difficult, mind-bending subjects in physics, quantum mechanics, and proposes a way to fundamentally simplify how we learn and calculate it. To really get what's happening here, we first need to understand what a term rewriting semantic actually is. So instead of relying on heavy calculus or massive, intimidating matrices, term rewriting acts kind of like a logical symbol game. You take a sequence of symbols, you apply a basic set of replacement rules to transform them, and boom, you get your answer. By mapping complex quantum states to this kind of simple rewriting system, this explainer is going to show you how the seemingly impenetrable wall of quantum mathematics is quite literally being dismantled. So here's a wild thought for you. Can middle schoolers calculate quantum states? Honestly, it sounds almost absurd on its face. We've got this common assumption baked into us that entering the world of quantum physics requires this massive, grueling upfront investment in complex math. And it makes sense why we think that, right? Because traditional quantum physics deals with continuous probability waves and infinite dimensional spaces. We're taught that you absolutely must master linear algebra and differential equations before you can even get your foot in the door. We've essentially been conditioned to believe that quantum calculations are strictly reserved for postgrads in fancy university labs. But guess what? That assumption is being completely challenged right now. By swapping out all that continuous, highly complex math for a discrete, rule-based approach, the actual mechanics of the quantum world can be broken down into something way more intuitive.
All right, let's move on to Section 1, the quantum math barrier.
Traditionally, first-time quantum learners just smack right into this massive wall of intimidating notation. Traditional quantum theory is incredibly heavy. It's mathematically demanding, and frankly, it acts as a huge barrier to entry. People hit this wall of abstract matrices and complex vectors, and they just give up. They quit before they ever get to experience the actual amazing physics happening underneath. But then we have the misty state picture, and this completely changes the game. Instead of advanced calculus, it relies entirely on an elementary rewriting system. Think of it conceptually like taking those giant, abstract algebraic matrices and just replacing them with simple string transformations and visual logic rules. You're essentially doing basic arithmetic to track how quantum information moves and changes. Just imagine stripping away all that complex notation and using basic counting and substitution rules to actually understand quantum computing. That is the exact promise of the Misty State framework.
Let's dive a little deeper in Section 2, Introducing Misty States.
To really grasp how we arrived at this new 2026 paper, it helps to take a quick look back at the timeline. Back in 2017, researcher Terry Rudolph introduced this incredible concept of representing quantum states as misty states. You see, Rudolph was looking closely at how quantum mechanics was taught, and he realized something profound. High schoolers were actually entirely capable of grasping the weird, counterintuitive concepts of quantum physics. What was stopping them wasn't the physics at all, it was just the math. So he invented misty states specifically to accurately describe the basics of quantum circuits to high school and middle school students using simple visual and mathematical rules. Fast forward to 2026, and Dan Adrian German has taken this foundational work and published a paper that significantly extends its semantics. So we're looking at nearly a decade of evolution here, refining a tool that bypasses math anxiety entirely and gets students straight to the mechanics. Now, you might be wondering, if we're teaching this using simple arithmetic, isn't this just some watered-down, inaccurate version of real physics? Well, the answer is absolutely not. This framework relies on a tiny, universal set of computational gates. And this small set is computationally complete, which means it can literally perform any quantum operation. It leverages these brilliant mathematical results by Yaoyun Shi, who proved that a very specific, minimal set of operations is perfectly sufficient to simulate any quantum circuit. On top of that, it builds directly on powerful proofs by A. Kitov. These proofs essentially guarantee that approximating these quantum states using simpler rules won't lead to some wild cascading series of errors. The simplified system maps perfectly to reality without breaking fundamental quantum logic, so it achieves highly accurate calculations without sacrificing the underlying precision of the science. It is definitely not a dumbed-down model. It's an incredibly rigorous translation. Which brings us nicely to Section 3, A Bridge to Conventional Math. The authors are super clear about their intent here. They state explicitly in the paper, and I'll just quote them directly, "We don't advocate that we should recast all of quantum theory into this formalism." The misty state picture is a good way of getting people to the heart of some non-trivial quantum theory without having to first absorb a huge amount of irrelevant math.
The goal here isn't to just burn down the traditional mathematics establishment, not at all. The MISTY formalism is a bridge. It's explicitly designed to facilitate a smooth transition to the full, conventional mathematical apparatus later on. Think about it. Once a student locks in the foundational concepts, like entanglement and superposition, they can then comfortably cross that bridge into the intimidating world of standard Dirac notation and complex Hilbert spaces. You learn the concepts first, you fall in love with the physics, and then you tackle the heavy math.
All right, let's get to the really exciting new stuff in Section 4, extending the formalism. Dan Adrian German's new work represents a massive expansion of this teaching tool, proving just how robust it is across really complex scenarios. Step 1. The paper reviews Rudolph's original proposal by showing it in action through entanglement swapping. If you don't know, entanglement swapping is this wild quantum phenomenon where two particles that have literally never interacted with each other become quantumly entangled by both interacting with a third intermediary partner. Demonstrating that with simple arithmetic sets a powerful baseline. Then, German extends the formalism by adding a completely new category of irreducible MISTY states that act as fixed points. Actually, think of irreducible states sort of like reducing a mathematical fraction. Once you simplify it down as far as it can possibly go, you reach a stable fixed endpoint. This addition gives the rewriting system so much more stability for complex calculations. Finally, German presents the famously complex GHZ game using this entirely new generalized setting. The GHZ game is this amazing multiplayer quantum thought experiment where players can win 100% of the time if they use quantum strategies, which is strictly mathematically impossible under classical physics. Proving the mechanics of the GHZ game using basic arithmetic and string rewriting, that is a staggering achievement. It absolutely proves this accessible framework can handle deeply complex multi-particle quantum scenarios.
So what does this all mean for us? Empowering first-time learners to compute pure quantum states using term-writing semantics fundamentally changes the entire landscape of physics education. Lowering this massive barrier to entry could rapidly accelerate the development of the future quantum workforce. We are literally talking about taking quantum computing out of highly specialized doctoral-level physics labs and moving it directly into undergraduate and even high school general computer science classrooms. It turns out, the barrier to entry was never the human brain's capacity to understand quantum mechanics. It was simply the complex mathematical language we were forcing people to read it in.
And all of this leaves us with a pretty profound question. How will term rewriting semantics revolutionize who gets to participate in the quantum computing revolution? If high schoolers can accurately map and grasp the mechanics of quantum circuits today using MISTY states and simple rewriting rules, just imagine the kinds of systems they're going to be building tomorrow. It also really makes you wonder, what other highly complex, math-heavy fields are out there just waiting for a similar structural translation to suddenly become accessible to the wider public? Thank you so much for joining me for this explainer on Dan Adrian German's incredible work. Stay curious, and I'll catch you next time.